Okay, so finishing up this problem. So we got to here, we decided it is not tan inverse because of the 6x. If it was just 6, it would be tan inverse. But the x up there messes it up for being tan inverse. We can't rewrite this to a non-fraction using negative exponents, so we came down with, can I make it look 1 over u du? And I can. We'll let u equal the denominator. And so u equal 4 plus x squared. Du would then be 2x dx. And dx would be du over 2. It's a definite integral. I'm going to calculate my new limits, because that's what I like to do. So new limits, x equal, it wasn't 0, it was x equal 1. U will equal 4 plus x squared, so 4 plus 1 squared, or 5. And x equals square root of 3. U, which is 4 plus x squared, will be that one's bad. Will be 4 plus the square root of 3 squared, which will be 7. And I'm just going to write this down again so I have a little more space. So this was going to be u. Dx was going to be replaced by du over 2. X. I forgot my x over here. Made a little mistake from here to here. Du would be dx would be du over 2x. And the reason I caught my little mistake here when I just put the 2, that x wasn't going to cancel and I knew something was going wrong. Remember, when you do a u substitution, you want everybody to get back to u. And so if I didn't have that x there, it's not that necessarily I wouldn't be able to fix it. It's just that I was really anticipating that that x should cancel. And indeed, when I make that correction, that x is going to cancel. And so the x's cancel. And so I've got 1 over 2 times the square root of e minus 1. That 2 can just factor out to the front. Then x equal 1 went to u equal 5. X equals square root of 3 went to u equals 7. So the integral from 5 to 7 of 1 over u du. And that I can easily integrate. That's the natural log of the absolute value of u from 5 to 7. And so that's going to be the natural log of 7 minus the natural log of 5 all over 2 times the square root of e minus 1. And as far as I'm concerned, you could absolutely leave it like that, or that's the natural log of 7/5 over 2 times the square root of e minus 1. And there's my good answer. No need to go back to x, because I bothered to calculate the u limits, so when I integrated, I could go directly to the evaluation. That is what I think is easiest. Okay, last thing in this section, and it's mostly just a cultural thing. We're not going to do anything with it. We're just going to state it and be done with it. But the last thing in this, one last thing I want to do. I want to actually, so this is the average value, and I didn't actually say what the average value is. But it literally is finding the average. That if you could take every number between 1 and square root of e, plug it into the function, get all those values, then add up those values and divide by the number of numbers, just like when you find an average. If you're finding an average of 5 numbers, you add them up and divide by 5. This is what this is doing. This is literally finding the average of this function. That if I could take every single number between 1 and square root of e, plug it in there, get all those answers, then add up all those answers, and then divide by the number of answers to get the average, that's what it's doing. because remember, the definite integral is really a Riemann sum. And remember those pictures, that we're filling those pictures with rectangles and letting those rectangles get smaller and smaller and smaller till each rectangle is really a line segment, then adding up the length of all those line segments. That's what the definite integral does. It adds up all those values. It's adding up every single value of f of x from a to b, and then when I divide it by 1 over b minus a, or when I multiply by 1 over b minus a, or divide by b minus a, that's giving me the average. And so it really legitimately is the average here of all the answers I could get by plugging into f of x, because of what the definite integral does. It is adding up all those values. Think of those rectangles getting smaller and smaller and smaller until they were line segments, and you were adding up the length of every single line segment. That's what the integral does. It adds up all those values, and then when I divide by b minus a, it comes out to be an average. So it really is the average value because of what definite integrals really are. Okay, then the last thing I need to say in here, the mean value theorem for integrals. This theorem is not as critical as the mean value theorem for derivatives, but we got it. If y equals f of x is continuous on a closed interval a to b, then at some point c in the closed interval a to b, f of c equals 1 over b equals f of c equals 1 over b minus a times the integral from a to b of f of x dx. Recall the average value is given by that, and notice that is in there. Zoom in a little bit so you can see it better. So there's the average value, which is in this definition here. And so all this is saying is that at some place in the interval, somewhere in a to b, there is some sort of number that when you plug it into the function, you will get the average value. Thus, the mean value theorem for integrals is saying if y equals f of x is continuous on the closed interval from a to b, there is some number in c, some number c in the closed interval a to b where f of c equals the average value of f of x. Now, it just says that number exists. It is not telling you what that number is or giving you any idea how to find the number. This is, in mathematical terms, what's called an existence theorem. It's just saying that if this guy is continuous on a closed interval a to b, then there is some sort of number, there is a number that exists that I can plug it into the function that would yield the average value. That's all I'm going to say about it. Like I said, we're not going to do anything with it. Kind of culture to end this video and to end this section.